Well, in these videos we want to think about the disorders of the circulatory system. So what we always like to do on these videos is start with some anatomy and physiology. So we'll start with the heart. So the heart's got valves pointing up the way just here, and this wall becomes thinner about here. Now these valves pointing up the way, these give rise to the large arterial vessels. This one is the aorta, the large vessel leaving the left ventricle. And there's a valve just here pointing down the way. And blood vessels actually enter this top chamber, the atria. So this is the left atrium here. There's actually 4 of these vessels, but we're just drawing a simplified diagram. Valve pointing up the way on the right side of the heart, again leading to a large vessel. This one's the pulmonary artery. Valve pointing down the way. And again the atrium at the top with blood vessels going into this. So we have the left atrium and the right atrium, the left ventricle and the right ventricle, the aorta and the pulmonary artery. This vessel here is going to be representing the pulmonary veins. This vessel here is representing the inferior and superior vena cava. This is the mitral valve, this is the aortic valve, this is the pulmonary valve, and that's the tricuspid valve. So that's the basic heart. Now the aorta is taking blood into the systems of the body. So here we have the systems of the body, represented by this mass of tissue. Now the systems of the body are going to include the digestive system, the renal system, the gastrointestinal system, the liver. And it also includes your legs and your arms and your brain. It's all the systems of the body here. So for this reason we call these the systemic arteries. So these are the systemic arteries. The aorta is the first of the systemic arteries. Whereas this artery is going to the lungs, so this is the pulmonary arteries. So we've got the systemic arteries here, the pulmonary arteries on this side. And as we've said, these are taking blood to the body. When the blood's been round about the body, it will go back in the venous return to the right atrium, but ultimately via the inferior and superior vena cava. The pulmonary circulation, of course, is going to the lungs, so this mass here represents the lungs. And we have the lungs. Then the vein draining, there's going to be a vein draining the lungs. 2 main veins from each lung actually drain back into the left atrium. And there we have the outline of the circulation. Now, it's worth just colouring this in a bit. Blood's going to go from the left atrium through to the left ventricle, and we draw this blood in red because it's fully oxygenated out through the aortic valve and into the body. As the blood goes through the body, it gives up some of its oxygen. So to represent the darker red deoxygenated blood, we have the blue, taking blood back to the right atrium, right ventricle, into the pulmonary artery, or the pulmonary arterial system, to go to the lungs. As it goes through the lungs, it's going to be oxygenated, so it's going to leave in fully oxygenated form. Going back to the left atrium. Now, a lot of the diseases of the circulatory system can be explained in terms of pressure changes in these vascular systems. So we've got the systemic arteries going to the systems of the body. So these veins here draining the body are the systemic veins. That's the systemic venous system. This system here, draining the lungs, this one, are the pulmonary veins. The pulmonary veins. Now, actually, of course, this is simplified. We could go on teaching this basic physiology forever, but basically, as you probably know, the arteries here are going to subdivide into lots of smaller branches, taking blood to all of the body, eventually becoming arterioles going into networks of capillaries. Then the capillaries are going to drain into venules, draining into larger veins, and eventually becoming the inferior and superior vena cava. And it would be a similar situation in the lungs. The pulmonary artery is going to break down into smaller branches, going into pulmonary capillaries, which are in very close proximity with the alveoli when oxygenated, and they're going to join up with other ones and eventually become the 4 pulmonary veins. So what we need to think about is the pressures now in these vessels. Now, the pressure in the systemic arteries is maybe 120/80. But of course, this is above atmospheric pressure. So we always have to 760 millimeters of mercury is the atmospheric pressure. So that's above atmospheric pressure. And we notice there's 2 pressures. 120/80. And that's because there's systole and disystole. Now, systole is when the ventricle is contracting, or ventricular systole is when the ventricles are contracting. So as this ventricle contracts, going to increase the pressure of the blood in the ventricle, ejecting the blood into the systemic arteries. And that's going to generate a pressure of about 120 millimeters of mercury. Then when the left ventricle finishes contracting, the time when the ventricle is not contracting is ventricular disystole, and the pressure is going to drop. But the pressure is maintained by the elastic recoil of the arteries. So the blood is going to be pushed into the arteries, but then because they're elastic, they're going to kind of spring back, maintaining the diastolic pressure. So 120 systolic, 180 diastolic. And of course, this blood has to go all around the body. It has to go to your, to your head, to your toes, everywhere. So we need a fairly high pressure. That's why the left ventricular myocardium, as we see here, is quite a thick muscle. As indeed is the muscle in the interventricular septum. Whereas the muscle on the right side of the heart is thinner simply because it doesn't have as far to pump the blood. It's much further to your toes and your head than it is just to go to your lungs, which are also in the thoracic cavity, of course. So the pressure in the pulmonary arteries might be 20/12. I mean, they're going to vary a bit, but there's that kind of pressure. So 20 millimeters of mercury when the right ventricle is in systole, when the right ventricle is contracting. 12 millimeters of mercury when the right ventricle is not contracting, during disystole. And we can also put pressure on the pressure figures on the veins. So, for example, in the pulmonary veins, The pressure here might be 12 to 14 millimetres of mercury. All these pressures are millimetres of mercury. And there's another pressure called the central venous pressure. The CVP. In the large veins here, and that might be 3 to 8 millimetres of mercury. 3, 4, 5, 6, 7, 8 millimetres of mercury, that kind of range. Now, the reason that the ventricles are contracting are to maintain blood pressure. So we need blood pressure. And blood pressure equals cardiac output times systemic vascular resistance. So the blood pressure is determined by the volume of blood pumped out and the resistance to that blood in the arterial system. Most of the resistance actually comes from the arterioles, the small blood vessels. And the cardiac output is equal to the heart rate times the stroke volume. So the heart rate is the number of times the heart is contracting per minute, and the stroke volume is the volume of blood pumped out by the left ventricle per contraction. And that works out at about 70 beats per minute times 70 mils, which is what the stroke volume is. So that gives us about 4,900 mils of blood pumped out per minute, and that actually is about the, give or take, it's 5 litres. Blood pumped into the systemic circulation, and that's pretty well the whole volume of blood being pumped into the... So all of this here represents the systemic circulation. And in the same way, this here represents the whole pulmonary circulation. So there we have the normal circulatory system. Now what I want to do now is look at some abnormalities of this system. And I think we'll start with the pulmonary arteries and work round. So for example, there's a condition called pulmonary heart disease. In the old days, this used to be called cor pulmonale. And there's two forms of pulmonary heart disease. But in both of them, the pressure in the pulmonary arteries is going to increase. So in pulmonary heart disease, there's going to be pulmonary hypertension. There's going to be increase in the pressure in the pulmonary arteries. And what pulmonary heart disease is, it's actually heart disease caused by a problem in the lungs. And there's two forms. It can be acute or it can be chronic. So there can be an acute pulmonary heart disease caused by an acute pulmonary hypertension, or there can be chronic pulmonary heart disease caused by a chronic pulmonary hypertension. Now the acute form, for example, can be caused by venothromboembolism. So if we look at the word, veno to do with the veins, thrombo, a thrombus is a blood clot where there should not be one, and an embolism is when that blood clot moves in the venous system. So very often venothromboembolism can be caused by a deep venous thrombosis. A deep venous thrombosis. And we can actually plot what happens here. Because in a deep venous thrombosis, the problem is going to start in the systemic veins. So there could be a blood clot in a vein here in the leg. And as an embolus breaks off that, it's going to go through the right side of the heart, through there. Now, if there's an embolus breaks off here, as it goes through these vessels, these are getting larger all the time. And the chambers of the heart are fairly large, so it can fit through there. But then when it comes to an artery that it can no longer fit through, it's going to get blocked off. It's going to block off a segment of the pulmonary circulation. So it's a thrombus there where it formed, then it embolizes, and it's the emboli that goes through the circulation. So let's just follow that again. From a systemic vein, draining through the systemic veins, right atrium, right ventricle, pulmonary artery, lodging in the pulmonary arterial system of the lungs. And then we would call it a pulmonary embolism. A pulmonary embolism. Now, how severe this condition is depends largely on how big it is. A huge one could block here. But I think you can see if it's blocking off the pulmonary circulation, that means the blood's going to be forced around other parts of the pulmonary circulation. So that means there's going to be back pressure, and it's going to increase the pulmonary arterial pressure if it's a large embolism. So that will be venothromboembolism presenting as deep venous thrombosis and pulmonary embolism. Of course, we normally say DVT can go to PE. Deep venous thrombosis can go to pulmonary embolism. Now, the chronic form, for example, can occur in chronic obstructive pulmonary disease, COPD. Now, what happens here is in chronic bronchitis, there's not enough air getting into the lungs. So areas of the alveoli are going to be low in oxygen. And when that happens in the pulmonary vessels, the low levels of oxygen cause a reflex pulmonary arterial vasoconstriction. So this is going to cause pulmonary arterial vasoconstriction. In the pulmonary vessels. It's going to be in the pulmonary vessels. Now, physiologically, that's good because it means that a lot of blood normally does not go to areas of the lung that don't have oxygen to pick up. So that's good. But in this situation, in COPD, all of the lungs are going to be involved. So there's a deficiency of oxygen in the alveoli all over the lungs. So that means all of the pulmonary vessels are going to close down. There's going to be a global pulmonary arterial reflex vasoconstriction in response to the reduced levels of oxygen in the alveoli. And if we constrict the vessels, that's going to increase the resistance, and that's going to increase the pressure in the pulmonary artery. So again, the COPD causing the vasoconstriction of the pulmonary vessels is going to lead to the pulmonary hypertension. And that's bad because over time, because the pressure here is high, the pressure in the pulmonary artery is high, is that going to mean the right ventricle has to work harder or less hard to pump the blood out? Well, if the pressure in here is high because of the vasoconstriction in the pulmonary arterial system, I think you can probably see that's going to increase the right ventricular workload. It's going to have to work harder. And if the right ventricle has to work harder, over time that's going to cause ventricular hypertrophy. And over time, that's going to lead to left ventricular failure. Sorry, right ventricular failure. let's just clarify that. The right ventricle has to work harder. That's going to cause right ventricular hypertrophy. There's going to be an overgrowth of the right ventricle. But over time, it's going to decompensate, and that's going to lead to right ventricular failure. Now, if we have right ventricular failure, the right ventricle is not pumping blood out properly anymore, then every time the right ventricle contracts, it's not going to be pumping out enough blood. So you're going to get blood left over in the right ventricle at the end of systole. Is that going to make it easier or harder for the blood to leave the right atrium? Well, if that's half full, it's going to be harder. So it's going to increase the pressure here. That's going to make it harder for the blood to drain out of the systemic veins. So we're going to get a back pressure here into the systemic veins. And we'll see that will lead to systemic edema, but we'll do that when we look at systemic veins. So there we have the pulmonary heart disease, the acute and the chronic form. But in both of them, there's going to be pulmonary arterial hypertension. Acutely because of the presence of the emboli, or chronically because of the vasoconstriction in the pulmonary arterial vessels induced by the low levels of oxygen in the alveoli, giving rise to chronic vasoconstriction, chronic increased pulmonary arterial pressure, ongoing chronic increased workload of the right ventricle, leading to right ventricular hypertrophy and then right ventricular failure. So in the next video clip, I think we'll go on and look at the systemic arteries.